Oh hey, I didn't even see you there. I'm Adam, welcome to my laboratory. Welcome back guys. Today our topic is chemistry. Let's go surprise our friend Ryan over here. See how he's doing. Shh, be very silent. What's up Ryan?
How you doing, Adam?
Finding yourself?
Good, good, good.
Guess what? Just take a guess, any guess.
Adam, I told you 1,000 times not to take a dump on that lawn. That really stinks. What?
Guess what we're teaching today?
I don't know.
Chemistry.
Chemistry?
Chemistry.
Woo, baby, let's do this, man. I mean, I ain't no doctor, but I know what's up about chemistry. Let's go.
Hey guys, my name is Garrett. This is our friend Ryan Gray here. We're going to interview him about what he knows about acids and bases. So tell us, Ryan, what do you know about acids and bases?
What's up, guys? We're going to be talking about acids and bases today. Let's do this. Okay, so I want to get into the basics of an acid and a base. Acids always contain a hydrogen. Not always, like always, but most of the time, 99% of the time, they're going to have hydrogen in it. With bases, it's going to be hydroxide, also known as OH. And then you're going to want to get into the properties of it. Properties. Okay, so with an acid, it's going to taste sour, and it's going to be really caustic to touch. It's going to be like almost as if dangerous if it were lower on the pH scale. But I'm going to get into that right now. But with bases, it's just bitter, slippery, and yeah, just like a really bitter taste and has like a slippery feel to it. And then, let's see here, the Bronsted-Lowry model. The Bronsted-Lowry model, that just basically says that an acid is a hydrogen donor and the base is the hydrogen acceptor, also known as shake and take. Just remember shake and take when you're thinking of the Bronsted-Lowry model. I'm sorry. So, I want to get into an example of an acids and bases problem. So, you're right here, right? You have hydrogen chloride and water turning into H3O and just chlorine by itself. So this is obviously the acid because it has hydrogen in it. And this is neutral, or as if in this problem it's the base. And it's going to be turning into, because obviously this is a conjugate acid. And this is the conjugate base. So the conjugate, it's always obviously called the conjugate acid because it takes the acid, so that's easy. Conjugate acid, it takes an acid. Conjugate base, it's just by itself. That's why it's called a conjugate base. And now we're going to be talking about a pH scale. What a pH scale is basically is that it ranges from 1 to 14 on the scale. It's okay, so a pH, that's 1 to 7, pOH, 7 to 14. The lower, so let's talk about the pH scale first, 1 to 7. So when you're, let's see here, when you have something really, really acidic, it's going to be in the lower, way lower, so like a 1, a 2, maybe. And if it's like not, it's like kind of a weak acid, it's going to be like in a 6, maybe 5. And then with the pOH, it's going to want to get higher if it's really, really basic. So a really, really basic example would be about a 14, 13, maybe even 12. And like not really that basic would be about like 8, 9, maybe. And then 7 is the neutral number on the scale because it can either act as an acid or a base, better known as amphoteric. And yes, that's basically what it is, an acid and a base. That's all you really need to know for today. Garrett, give me an example of a base. Garrett, why do you carry soap on you, buddy? This is obviously like a base example because it's slippery. If you were to put it in your mouth for bad language, it's bitter. And yeah, soap is like a great example of a base. Toss me an acid, buddy. It's an example of an acid. It's an orange, really like sour, kind of sweet. Sour and yeah, sour and acidic, buddy.
Alright guys, today I'm going to be teaching you guys about the periodic table of elements. Okay, first off, there's a specialized group of elements in each periodic table. For example, the first row, or the first group, is called alkaline metals. All of them are alkaline metals except for hydrogen. I have no idea why.
Adam!
It pisses me off. Oh man.
Sorry for the delay, folks. Adam has some time off for his fellow language and behavior. Anyways, back to the periodic table. Periodic table is pretty much organization of all the elements you'll need to know for everything consistent with chemistry. First of all, the groups. Groups are up and down, periods are left and right. There are 8 groups. Well, there are more than 8 groups, but only 8 groups I count because the rest are transition metals. The periods are only 7 periods. 1, 2, 3, 4, 5, 6, 7. Now we're talking about the specific group names for all the group numbers. The first group is alkali metals, as right here. It only counts 2 through 7 because hydrogen, I don't know why, it just isn't an alkali metal. Group 2 is alkaline earth metals. These are the only, these are the only elements on the left side that have positive charges, like for example, positive 1, positive 2. Now on the right side, group 8 is the noble gases. These are very stable gases. You don't want to react with any other element because they already have 8 valence electrons. We'll get into that later. So they're perfectly stable and they're perfectly fine. Group 7 is the halogens. These are usually the most reactive elements, especially fluorine, because it has 7 valence electrons and it wants 1 more to become very stable. So it tries very hard to get 1 more. And then right here, the staircase, you can see like B, SiG, AS, SB, TE, and PO. Those are the metalloids or semi-metals, as you can see. And these charges right here, -1, -2, -3, they go down. They go kind of opposite order from the left side. Like this one goes left to right, that goes right to left. And then these middle right here, 3 through 12, these are all transition metals. And right here, these are just left out because the organization, the periodic table would have been too long or wide. So this is the lanthanide series. These are the actinide series. And all these elements are just made up in laboratories because they're not naturally found. And so let's go on back to valence electrons. Valence electrons pretty much like what defined element. So if CF has 1, it's not very reactive. But if it has like 7 like this one, it is very reactive. So like 1 valence electron, 2 valence electrons, 3, 4, 5, 6, 7, 8. So you can see noble gases already have 8 valence electrons. That's what every element needs. Now back to like each element for itself. Like say like right here is hydrogen. That is the element symbol. Say like lithium's Li, beryllium is Be. So each one has like its own like symbol for each one. And then above it, as you can see right here, is 1 has a proton and the electron number in the element. And right below it is an atomic mass. Not all the atomic masses are going to be the same exact, because some can be naturally different, or they can be like in a laboratory, they can be designed to have different masses. The number of neutrons is the average atomic mass, like right here, 23 minus 11, so that'd be 12 neutrons. And there can be isotopes, which is just different number of neutrons, and ions are just different charges. And so also the trends, ionization energy, fluorine is the greatest one. That just means that it wants another valence electron or wants another electron into itself. The least most ionization element is francium. This is only one. It's so big. The radius of the element is so big. It just doesn't like it's hard for it to attract another electron. So that's pretty much the periodic table in a jiffy. I'm Garrett. Talk to you later.
Guys, now that I'm back from my timeout, I'm going to make that mistake again. We'll be talking about phase changes and states of matter. Solid, liquid, gas. Gas, liquid, solid. Solids, the intermolecular forces are very strong, which is why the molecules are tightly compact, and the only way they can move is by vibrating. Solid, it can be anything, a rock, anything solid that's just hard. Liquid. Intermolecular forces are weak, which is why they can move around, they're free. They can fill any container, you can move it around. Yeah. Gases, gases, there are no intermolecular forces, which is why they just randomly move any way they want, freely. They dissolve with anything. They fill any container. And yeah, that's it. Okay, alright guys, now next step, I'm going to show you guys 6 different phase changes. Right, if you please come over here.
Stop calling me that!
Alright. Solid to liquid, melting. Melting, you got that? Liquid to solid, freezing. I'm pretty sure most of you guys already knew that. It's the basics. I'm just re-installing that in your head. Okay, and if you go from a liquid to a gas, liquid to gas, evaporation. Got that? Evaporation. So say you're boiling water and the steam that's coming out of that, it's evaporating. Okay? Gas to a liquid is condensation, which is when the gas, okay, say you have water boiling and you put plastic on top of the steam. The steam would eventually collect and then it'd start form liquid, which is why rain happens. Because when rain happens, the liquid is evaporated into gas, and then the gas forms into condensation, which turns it back into liquid, which is why it rains. Okay, gas to solid, deposition from a gas to a solid. So you're skipping the liquid phase, and you're just going from a gas to a solid. From a solid to a gas, it's called sublimation. Got that? Sublimation. Alright, and now, coming up, you guys are going to see some examples of solids, of the dangers of solids, liquids, and gases. They all have dangerous effects, and they can all kill you.
Here you go, Adam.
Oh, thanks, man. I'm really thirsty. Yes, he's dead. Yes.
Guys!
We're back here with Ryan.
Don't touch me.
Sorry, bro. Alright, now we're going to be talking about nuclear chemistry.
Wait. Nuclear chemistry, wasn't that the kind of stuff with that movie? Have you seen Hills of Eyes?
Yeah.
Was that like mutations, radioactivity? Is that nuclear chemistry basically?
Kind of.
Okay. Okay, I got the hang of you. Wait. Oh, that new movie, Charbold Diaries, or the kind of like paranormal.
Oh yeah, right.
Okay.
Alright.
I know what we're talking about. All right. Okay. Stuff. Let's go.
All right. Tell me what you know about fusion.
Fusion. Okay, fusion is when you have one atom and another atom, and they come together forming just one atom, and there's like a whole bunch of energy, and yeah, it just creates a ton of energy. And what's
Very good. What about fission?
Fission is basically the opposite, and that is when you have the atoms just split. So like they come together, they split forward, and they just come into two.
All right, let's go. Get the point.
Okay.
Took forever. All right. What are the? All right. How can you? How can I put this? All right. How is fusion and fission used in everyday life?
Okay, well, first of all, fusion, it's all, no, not naturally, why would I say that? It's just always occurring in the sun. That's basically what the sun is. They should just name it fusion because it's always happening in the sun. That's what basically gives us the energy of what we're getting right now from fusion and all like that radioactivity, nuclear bombs and all.